December 18, 1942, Aberdeen Proving Grounds, Maryland. The air hung heavy with anticipation as a line of military officials and engineers shivered in the biting winter cold. Lieutenant Colonel James Wilkinson checked his watch for the fourth time in 5 minutes, his breath forming clouds in the frigid morning air. The demonstration was about to prove that his unorthodox armor solution would revolutionize Allied tank production, or reveal him as a fool who wasted precious wartime resources on scrap metal. Little did these men know they were about to witness a turning point in armored warfare that would ultimately save thousands of American lives and help turn the tide of the war. Before we dive into this story, drop a quick hi in the comments and tell me where you're watching from. It really helps support the channel. This is the remarkable story of how desperation, scientific inquiry, and industrial ingenuity transformed what was literally considered garbage into one of the most effective armor systems of World War II, forever changing our understanding of battlefield protection and revealing how innovation often emerges from the most unexpected places. The winter of 1942 had been particularly difficult for the Allied forces. German U-boats were sinking merchant ships at an alarming rate, creating critical shortages of strategic materials across the United States and Britain. Among the most concerning was the dwindling supply of molybdenum, tungsten, and high-grade nickel, essential elements for producing the armor plate needed for tanks and warships. Major Howard Fleming, a metallurgist who had been working at the Bethlehem Steel Corporation before being commissioned into the Army's Ordnance Department, slammed his hand on the desk in frustration. "These specifications are impossible to meet with current material shortages," he told his team of engineers. "The Germans have access to the Swedish iron mines, and the Japanese have cut off our rubber and tin supplies from the Pacific. We're running out of options." Fleming's assistant, Lieutenant Sarah Harrington, a former chemical engineer from MIT and one of the few women in the Ordnance Department, looked thoughtfully at the scattered papers. Before the war, she had worked on recycling industrial waste products, a field considered unimportant until resource scarcity became a national security issue. "What about using something unconventional, sir?" Harrington suggested hesitantly. "I've been reviewing some old metallurgical studies from the Depression era, when manufacturers couldn't afford prime materials. There were some interesting results when using heterogeneous metal mixtures, essentially scrap, under specific heat treatment conditions." Fleming looked at her skeptically. "Lieutenant, we're talking about armor that needs to stop a Panzer shell, not some academic experiment." "With respect, sir, the problem isn't just about hardness," Harrington countered. "The current armor is brittle. It might stop the first hit, but it shatters. What if we could create something with more structural complexity that absorbs energy differently?" Across the Atlantic, the British were facing similar challenges. Squadron leader William Thornton of the Royal Armoured Corps had been collecting reports from the North African theatre that painted a disturbing picture. The British Crusader tanks, though faster than their German counterparts, were proving dangerously vulnerable to enemy fire. "It's a bloody disaster," Thornton told his American liaison, Captain Robert Dawson, during a secure transatlantic telephone call. "Our boys call them Tommy Cookers because of how quickly they burst into flames when hit. The armor simply isn't holding up against the German 88s. Dawson made notes as Thornton continued. "What's particularly interesting is that we salvaged a knocked-out German Panzer III last month. Their armor isn't necessarily thicker than ours, but it's performing better under battlefield conditions. There's something different about the metallurgical composition." Meanwhile, at the United States Steel Corporation's research facility in Pittsburgh, Dr. Marcus Weber was reaching similar conclusions through a completely different path. Weber had been studying the structural integrity of metal from demolished buildings and bridges that were being recycled for the war effort. Something unusual had caught his attention. "Some of these older structures are showing remarkable resilience," he explained to his colleague, Dr. Eleanor Hughes. "This I-beam from a 1912 factory building withstood stresses that should have sheared it completely. Look at the crystalline structure under the microscope." Hughes peered into the microscope and saw what resembled a complex web rather than the uniform patterns typical of modern steel production. "It's heterogeneous," she observed. "Multiple types of metal alloys interacting at the molecular level. But why would older steel perform better? Because, Weber replied, his eyes lighting up with realization, early 20th century steel production wasn't as refined or pure as our modern methods. There were more impurities, other elements that we now carefully remove. But what if those impurities were actually creating beneficial properties we've been engineering out? By February 1943, these separate threads of inquiry began to converge. Fleming had reluctantly authorized Harrington to conduct limited experiments using reclaimed metal. The results were promising enough to secure a meeting with Colonel Wilkinson, who oversaw armor development for the Ordnance Department. "So you're telling me," Wilkinson said, eyeing the samples on his desk with open skepticism, "that this hodgepodge of recycled metal, this junk, performs better than our precision-engineered armor plate?" "Not in all conditions," Harrington clarified, "but in specific ballistic tests, yes. The heterogeneous composition creates multiple microscopic barriers that distribute impact energy differently than homogeneous plate. It's less likely to crack catastrophically." Wilkinson wasn't convinced. "And where exactly would we source this miracle material? We can't exactly ask factories to produce imperfect steel." Fleming stepped forward. "That's the surprising advantage, sir. We can use scrap. Demolished buildings, old railroad tracks, even salvaged automobile frames. Material that doesn't meet the stringent requirements for conventional armor production suddenly becomes viable." The potential implications were enormous. The United States was producing approximately 6 million tons of scrap metal annually, material that was being recycled but often downgraded to less critical applications due to inconsistent quality. If even a portion of this could be repurposed for armor production, it would significantly reduce dependence on limited strategic alloys. Across the Atlantic, the British were making similar discoveries. Thornton had connected with metallurgists at Birmingham University who had been studying armor fragments recovered from battlefields in North Africa and Russia. Their findings aligned with the American research. Armor with greater structural complexity at the molecular level was demonstrating superior performance against certain types of projectiles. Professor Alan Richardson of Birmingham University explained the phenomenon to a gathering of Ministry of Supply officials. Conventional armor relies primarily on hardness to defeat incoming projectiles, but there's a fundamental trade-off. The harder the metal, the more brittle it becomes. What we're seeing in these samples is a different approach. The heterogeneous composition creates multiple energy-absorbing boundaries at the microscopic level. The projectile's energy is dispersed rather than transmitted directly through the plate. The officials exchanged skeptical glances. One of them, Sir Roger Pennington, voiced what many were thinking. "Are you seriously suggesting we armor His Majesty's tanks with what amounts to metallurgical leftovers?" Richardson remained undaunted. "I'm suggesting that we've been operating under assumptions about material purity that may be counterproductive for this specific application. Nature rarely creates pure homogeneous structures. Think of how wood or bone derives strength from complex, varied compositions." Back in the United States, the concept was meeting similar resistance. The established armor manufacturers had invested millions in facilities designed to produce homogeneous steel plate to exacting specifications. Introducing a fundamentally different approach threatened both their expertise and their production methods. Carnegie Steel executive William Harrison was particularly vocal in his opposition during a War Production Board meeting in Washington. "Gentlemen, this is madness," he declared. "We've spent decades perfecting armor production based on scientific principles. Now we're being asked to believe that random scrap metal, melted together without precision control, will somehow outperform our engineered product? It defies logic." Dr. Weber, who had been invited to present his findings, remained calm. "Mr. Harrison, I understand your skepticism, but I invite you to consider that many of our scientific principles are actually relatively recent assumptions. The metallurgy of armor is still evolving. The Germans have already incorporated some of these principles in their tanks, whether by design or circumstance." The debate might have remained academic if not for a development from an unexpected quarter. Naval Lieutenant Commander Jason Parker had been overseeing armor testing for a new class of destroyer escorts when he noticed something strange. A test plate that had been rejected due to manufacturing defects unexpectedly outperformed regulation plates against certain projectiles. Parker, curious by nature, had the anomalous plate analyzed and discovered it contained unusual inclusions, essentially impurities that should have been removed during refining. He contacted the Bureau of Ships, which put him in touch with Fleming's team at the Ordnance Department. By April 1943, enough preliminary evidence had accumulated to warrant a comprehensive testing program. Colonel Wilkinson, though still skeptical, recognized the potential strategic advantage. He authorized a series of ballistic trials at Aberdeen Proving Grounds to compare conventional armor with plates produced using the new heterogeneous composition approach. The preparations for these tests revealed the deep institutional resistance to innovation. Major Thomas Garfield, who oversaw the testing facility, made little effort to hide his disdain. "So we're testing garbage metal now," he remarked to Fleming as they prepared the range. "What's next? Papier-mâché tank hulls?" Fleming had grown increasingly confident in the approach as additional data came in. "Major, I understand your skepticism, but remember, we're fighting a war where material shortages are as dangerous as enemy action. If this works, we can produce more armor with fewer critical materials." The test setup was rigorous. 3 different types of armor would be subjected to identical ballistic challenges: conventional homogeneous armor plate, face-hardened armor similar to German designs, and the experimental heterogeneous composite armor developed from the junk metal research. Among those present for the tests was Sergeant Frank Kowalski, a tank commander who had survived the brutal fighting in North Africa, only to be sent home after his Sherman tank was penetrated by German anti-tank fire, killing 3 of his crew. His presence was a stark reminder of the human cost of armor failures. "I don't care what it's made of," Kowalski told Fleming before the tests began. "I just care if it keeps my boys alive. Those panzers are cutting through our tanks like they're made of tin." The first rounds of testing produced mixed results. Against certain projectiles, particularly those striking at direct angles, the conventional armor performed adequately. But as the testing protocols began to mimic real battlefield conditions, oblique angles, multiple impacts, varying temperatures, the heterogeneous armor began to show distinct advantages. Lieutenant Sarah Harrington meticulously documented each test result. "The key difference," she explained to Colonel Wilkinson as they reviewed the data, "is in failure mode. Conventional armor tends to shatter or create spall, fragments that break off inside the vehicle, becoming deadly projectiles themselves. The heterogeneous armor absorbs and distributes energy differently. It might deform more, but it fails more gracefully, if you will." The most dramatic moment came during the sequential impact test, where plates were struck multiple times in close proximity. The conventional armor catastrophically failed after the second or third hit, while the heterogeneous plates withstood 5 or more impacts before being compromised. Sergeant Kowalski watched these tests with growing interest. "That's more like real combat," he commented. "Jerry doesn't just hit you once and call it a day. They keep firing until you're knocked out." By June 1943, the test results were conclusive enough to warrant expanded production trials. The War Production Board authorized 3 steel mills to adapt their processes to produce what was now being called composite heterogeneous armor, or CHA. This is where the real challenges began. Modern steel production was designed for consistency and purity, precisely the opposite of what the new armor required. Engineers had to essentially redesign production methods to maintain controlled heterogeneity, a concept that many metallurgists found almost heretical. At Republic Steel's Cleveland Works, production engineer Harold Mitchell struggled to explain the new requirements to his floor supervisors. "So let me get this straight," said shift manager Ray Donnelly. "After years of you riding my back about purity levels and homogenization, now you want me to deliberately introduce variation? Make up your mind." Mitchell sighed. "I know it sounds backward, Ray, but this isn't random variation. It's controlled heterogeneity. We're creating a specific type of structural complexity at the microscopic level. Think of it as deliberately engineering a certain kind of imperfection." Donnelly remained skeptical. "And this is supposed to stop German shells better than our regular armor?" "That's what the tests show," Mitchell confirmed. "But more importantly, It allows us to use a wider range of scrap inputs without requiring as much nickel, molybdenum, and other critical alloys. We can produce more armor with the same limited resources. Meanwhile, the British had been conducting their own trials at the Military Vehicles and Engineering Establishment at Chertsey. Their results paralleled the American findings. The heterogeneous armor compositions showed particular promise for certain applications, especially where multiple impact resistance was critical. The British approach differed somewhat from the American. Rather than using diverse scrap sources, they focused on deliberately introducing specific types of disruptive elements into otherwise conventional steel. The resulting disrupted matrix armor, DMA, performed similarly to the American CHA while being somewhat easier to quality control in production. By August 1943, the first production runs of CHA were ready for field testing. The initial application was not for tanks, as many had expected, but for armored personnel carriers, specifically the new M3A1 half-track. These vehicles had proven particularly vulnerable to German anti-tank rifles and light anti-tank weapons in Sicily and Italy. Captain Michael Donovan, commanding a company equipped with the new CHA armored half-tracks, wrote in his after-action report from Italy, "Engaged by enemy anti-tank rifles near Salerno beachhead, Vehicle number 3 took 3 confirmed hits from what appears to have been a Panzerbüchse 39. Armor was penetrated only on the 3rd hit, and even then, damage was limited compared to previous experiences with similar weapons. Crew survived with minor injuries." Similar reports began to accumulate from various fronts. While the new armor wasn't invulnerable, no armor ever is, it was demonstrating significantly improved performance against certain common threats, particularly the smaller caliber weapons that infantry units frequently encountered. The success with half-tracks led to expanded applications. By late 1943, sections of CHA were being incorporated into the M4 Sherman tank, particularly in areas that had proven vulnerable in combat. These applique armor packages could be field retrofitted to tanks already in service, providing immediate benefits without requiring complete redesigns. Tank crews quickly noted the difference. Sergeant William Thornton of the 297th Tank Battalion wrote home, "They gave us this new armor plating last week. The boys are calling it magic metal because of the stories going around about what it's made from. Some say it's melted down German tanks, others think it's some new secret alloy. Whatever it is, Jenkins in 3rd Platoon swears it saved his life when they got hit by a Panzerfaust outside Caen." The rumors surrounding the new armor grew increasingly elaborate as its reputation spread. German intelligence reports began to mention the mysterious new American armor that seemed to resist their anti-tank weapons with unexpected effectiveness. Some German commanders even speculated that the Americans had reverse-engineered captured German armor or developed an entirely new metallurgical process. The reality was both more mundane and more remarkable. By early 1944, the production of CHA had expanded dramatically, incorporating an ever wider range of input materials. Old bridges, demolished buildings, even salvaged automobile frames were being transformed into armor that was saving lives on the battlefield. Dr. Eleanor Hughes, now overseeing quality control at the Carnegie Steel CHA production facility, maintained meticulous records of input materials and performance results. "What we're learning challenges fundamental assumptions about metallurgy," she told visitors from the War Production Board. "It turns out that structural complexity at multiple scales, from the microscopic to the macroscopic, creates emergent properties that we couldn't predict from standard materials science." The success of CHA and its British equivalent, DMA, led to increased investment in what was now being called heterogeneous materials science. Researchers began exploring applications beyond armor, from aircraft structural components to naval bulkheads. By D-Day, June 6, 1944, approximately 30% of American armored vehicles involved in the Normandy landings incorporated some form of heterogeneous armor. The improved survivability became particularly evident during the hedgerow fighting in the days and weeks following the invasion, where German infantry armed with Panzerfausts posed a constant threat to Allied armor. Captain Robert Dawson, now commanding a tank company equipped with CHA-enhanced Shermans, wrote in his unit log, engaged by multiple Panzerfausts during advance towards St. Lo. 2 direct hits on Alpha 3's left side and turret. Damage was significant, but non-catastrophic. Crew survived and vehicle remained operational enough to withdraw under its own power. Previous experience suggests such hits would likely have resulted in complete vehicle loss and crew casualties. The development of heterogeneous armor also spurred German countermeasures. By late 1944, German anti-tank units were receiving updated ammunition designed to defeat the new Allied armor. This technological escalation was a pattern familiar throughout military history, innovation followed by counter-innovation in an endless cycle. What made the heterogeneous armor story particularly remarkable was its origins in material shortage and scientific open-mindedness. It represented a fundamental shift in thinking about materials, from an emphasis on purity and homogeneity toward an appreciation for structured complexity. Dr. Marcus Weber, presenting his findings to the American Society for Metals in December 1944, put it this way: "For decades we've been refining our metals to greater and greater purity, assuming that uniformity equates to quality. What we've discovered through this work is that nature doesn't necessarily favor homogeneity. The most resilient natural materials, wood, bone, shell, derive their extraordinary properties from structural complexity at multiple scales." The implications extended beyond wartime applications. As the conflict in Europe moved toward its conclusion, engineers and scientists began considering how the principles of heterogeneous materials might be applied to civilian products, from automobile bodies to building materials. Lieutenant Sarah Harrington, who had been promoted to captain by early 1945, was already looking ahead to peacetime applications. "The principles we've discovered have implications for sustainability as well as performance," she wrote in a report for the War Production Board. "By utilizing diverse input materials, effectively what we previously considered waste or suboptimal, we can create products that not only perform better but require fewer virgin resources." The final validation of the heterogeneous armor concept came during the last major German offensive, the Battle of the Bulge in December 1944. The brutal winter conditions and fierce fighting put every aspect of Allied equipment to the test. Tank crews reported that the CHA-enhanced vehicles performed particularly well in the extreme cold, where conventional armor sometimes became dangerously brittle. Staff Sergeant Paul Mendoza, a Sherman tank commander with the 4th Armored Division, later recalled, "We took a direct hit from what must have been an 88 during the relief of Bastogne. It punched through the main glacis plate, but the way it failed was different. It didn't shatter and spray the inside with fragments like I'd seen happen before. The armor sort of absorbed it somehow. 3 of us walked away from what should have been a coffin on tracks." As the war in Europe wound down, the lessons of heterogeneous armor development were being systematically documented and analyzed. The final report of the Joint Anglo-American Armor Commission, submitted in March 1945, concluded, "The development of composite heterogeneous armor represents one of the most significant metallurgical advances of the war period. Beyond its immediate military applications, it has opened new avenues of material science research that may ultimately prove as valuable in peace as they have been in conflict." Colonel James Wilkinson, who had initially regarded the concept with such skepticism, became one of its most vocal advocates. In his address to graduating engineering students at MIT in May 1945, he reflected, "The story of this war will eventually be told not just in terms of battles won and lost, but in terms of how we adapted, innovated, and overcame seemingly insurmountable challenges. The armor that protected our men didn't come from some secret laboratory breakthrough. It came from recognizing value in what we had previously discarded. There's a profound lesson there, beyond metallurgy. The end of World War II didn't end the development of heterogeneous materials. In the post-war period, the principles pioneered in wartime armor production influenced civilian manufacturing in countless ways. The strict dividing line between prime and secondary materials began to blur as engineers recognized that complexity and diversity at the microstructural level could create desirable properties impossible to achieve through traditional methods. Dr. Eleanor Hughes, who went on to head materials research at a major American automobile manufacturer, often pointed to the CHA development as a turning point in her field. "Before the war, we evaluated materials primarily on their purity and uniformity," she explained in a 1953 interview. "After our experience with heterogeneous armor, we began to consider structural complexity as a positive attribute to be engineered rather than an impurity to be eliminated." This fundamental shift in thinking has implications for everything from consumer products to infrastructure. For the men who fought in tanks and armored vehicles, the technical details of metallurgy mattered less than the protection it provided. Decades after the war, at a reunion of the 11th Armored Division, former tank commander Frank Kowalski raised a toast. "To the eggheads who figured out how to turn junk into armor, and to the factory workers who built it. A lot of us came home because of you." Perhaps the most lasting legacy of the heterogeneous armor story is its demonstration of how innovation often emerges from constraint rather than abundance. It was precisely the shortage of conventional materials that forced engineers and scientists to question fundamental assumptions and explore unconventional approaches. In the decades following World War II, the principles of heterogeneous materials science would influence developments ranging from composite aircraft structures to impact-resistant building designs. The recognition that structural complexity could create emergent properties impossible in homogeneous materials opened entirely new avenues of research and development. Today, advanced computer modeling allows materials scientists to design heterogeneity at precisely controlled scales, creating materials with properties tailored for specific applications. But the fundamental insight, that complexity and diversity at the microstructural level can be advantageous rather than detrimental, traces its practical origins to those desperate wartime experiments with junk metal. The story of heterogeneous armor development also illustrates how battlefield necessity can accelerate scientific progress. Concepts that might have taken decades to evolve in peacetime were compressed into months of intensive research and testing, driven by the urgent need to protect lives and conserve scarce resources. For the engineers and scientists involved, the experience was transformative. Many went on to distinguished careers in materials science, bringing with them the lessons learned from their wartime work. Their willingness to challenge established thinking and explore unconventional approaches set a powerful example for future generations of researchers. As Dr. Marcus Weber reflected in his memoir, published shortly before his death in 1972, "The most valuable scientific discoveries often come not from finding what we're looking for, but from being willing to see what's actually there, even when it contradicts our expectations." The story of heterogeneous armor is fundamentally a story about intellectual humility, about recognizing that our most cherished assumptions might be incomplete or even incorrect. The tanks and armored vehicles that incorporated heterogeneous armor have long since been retired, many of them melted down and recycled into new forms. But the scientific principles they helped establish continue to influence how we understand and design materials for countless applications. And perhaps most importantly, the thousands of servicemen who returned home safely because of this innovation went on to live full lives, raise families, and contribute to the post-war world in countless ways. Their untold stories, the books written, businesses built, children raised, and communities served, represent the true legacy of what began as a desperate experiment with junk metal. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II, and check out the video on screen for another incredible tale from history. Until next time.